Hello everyone and welcome. In today's video, I'm going to show you how to solve this problem. Let's look at the problem. A 25 kilogram wagon, including its load, is pulled along the level ground by a rope inclined at 30 degrees above the horizontal. A retarding force of 30 newtons opposes the motion. How large is the pulling force? If the wagon A is moving with a constant speed, and then B, if the wagon is moving at an acceleration of 0.40 meters per second squared. Let's look at the solution. To solve this problem, let's first look at this diagram here on the top right. We can see a wagon that is being pulled by a force F that makes an angle with the horizontal theta. So the horizontal or the level ground is our dashed line. So that pulling force makes an angle of theta with that horizontal. So there is going to be component of this force. And these components are going to be the horizontal component, which we can call Fx, and then a vertical component, which we can call Fy. Now, to resolve this, we can see that if you take the rope being the hypotenuse of this triangle, and then the Fx component of this force F as the adjacent side of this triangle, the Fy component of this force as the opposite side, we can have a right triangle. Therefore, we can apply Pythagorean theorem and also use trig to relate Fy, Fx, and theta. So Fy, since this is the angle of interest, the opposite side is going to be Fy and the adjacent side is going to be Fx. Now Fy, since it is the opposite side, it means the Fy component of this force or the vertical component of this force is going to be the force F sine of the angle theta. In the same sense, Fx is going to be the adjacent side, so we apply the cosine of the angle. So that is going to be F cosine of the angle theta. So now we know that this Fx and Fy, if we sum them vectorially, okay, using Pythagorean theorem, we are going to see that it is going to the length of Fx squared plus the length of Fy squared is going to be the length of F squared. Also, with this wagon, since the wagon and its load have a total mass, we are going to have the weight of the wagon pointing vertically downwards. So the weight of the wagon is going to be mass times acceleration due to gravity. And in reaction to this, there's going to be normal force, which is N pointing upwards. Remember, we are told that there is a retarding force which opposes the motion. That retarding force is going to point to the left, and that is our friction force between the floor or the ground and the tires of this wagon. Now we know all the forces that are acting on this object. We need to draw a free body diagram. Let's see how to do that. So a free body diagram is a simplified model where we isolate this whole wagon as a point particle and then indicate all the forces acting on this point particle with arrows. Now we know from this analysis here we just did, we know all the forces that are acting on this wagon. So let's model this wagon as a point particle. But before we do that, we need to specify our coordinate system so we can track the direction of each force acting on this wagon. So I'll go with the Cartesian coordinates. In that case, we just have the simple XY axis where all the forces acting vertically are going to be along the y-axis. And if the force is pointing upwards, then we are going to have a positive force. If it is pointing downwards, which is the opposite direction, would be negative. All right. In the same sense, all horizontal forces that point to the right, we are going to take that as positive direction. And then those pointing opposite to that are going to be the negative direction. Now, to represent this wagon as a point particle, I'll use a dot. So we have our wagon here. Now let's look at all the forces that are acting on that. So we know vertically there's the weight of this wagon. So the weight of this wagon, which is mg. And then the normal force, which is pointing upwards, is going to be N. Now, to the right, we have the horizontal force, which is Fx, that we found to be F cosine of the angle from here. And then we have another vertical force, that is the vertical component of the pulling force, which is Fy. And we found that to be F sine of the angle theta. Again, the retarding force points opposite to the horizontal force, and that we found to be Fr. So this here is a free body diagram. To solve this, we need to consider Newton's second law. What does Newton's second law say? It says that the net force acting on this wagon equals to the mass of the wagon times net acceleration produced from these net force. So that is Newton's second law. We will apply this to the first part of the problem. So A, when the object is moving with constant speed, what this means is that acceleration is 0. When the net force on an object is 0, it means that there is no acceleration and then the object moves at a constant speed. So let's apply Newton's second law for this part. If we say the Newton's second law says the net force acting on the object is equal to ma and acceleration is 0, then we will have the net force acting on this object being the mass times 0 acceleration, which gives us 0. But what are the forces along the horizontal direction? Because we have a knowledge that the wagon is moving horizontally. So we need to consider all the horizontal forces, that is along the x direction of our coordinate system. So if you look at the free body diagram, we can see all the forces that are pointing in the horizontal direction. In that case, we have Fx to the right, so it is positive, and then to the left, we have the retarding force, which is Fr, and that is equal to 0. So this left-hand side here is our net force because we have summed all the forces that are acting on this wagon. Okay, since speed is constant, it means the acceleration is 0, so the right-hand side is 0. We found the Fx to be F cosine theta using our trig from this part. So in that case, F cosine of theta minus the retarding force is equal to 0. Our goal is to find the pulling force, F, right? So if we need F, and we know that here we have F cosine theta minus the retarding force is equal to 0, we can easily isolate F, all right? To do that, we will first move the retarding force to the right-hand side, and then that will give us F cosine theta is equal to Fr. So it is negative here. So if we move it over there, it becomes positive. All right. So that is why here we have positive retarding force. Now, what can we do next is to divide both sides by cosine of theta, because we need to isolate just the pulling force. So cosine of theta here divided by cosine of theta here. So we balance the equation. So this cancels that. We are left with just the pulling force on the left-hand side. Now we can plug in the values since we know the retarding force Fr to be given as 30 newtons. And then we know theta to be given as 30 degrees. So to do that, we have 30 newtons in the numerator divided by the cosine of 30 degrees. So that is going to give us 30 newtons divided by 0.866. So the pulling force, if we evaluate this, is going to be about approximately equal to 34.6 newtons, which we can round it off to 35 newtons. All right. So we can see that for the first part, since the object is moving at a constant speed, the condition that the acceleration is 0 must hold. And we can see clearly the difference between the pulling force and the retarding force is about 5 newtons. And it is this 5 newtons that is just enough to set the wagon into constant speed motion. All right. If you have any question up to this stage, please comment it down below, and then I'm going to look at the second part of this problem. So for the second part of this problem, we have acceleration A equals 0.40 meters per second squared. Now let's apply Newton's second law again when the acceleration is not 0. In that case, the net force, sum of all the forces, equals ma. And acceleration this time is 0.40 meters per second squared. Now let's look at the forces that are acting on this object horizontally. So we go back to our free body diagram, which we see that is Fx to the right, so positive, minus the retarding force to the left, so negative, equals the mass of the wagon and the load times the acceleration produced. Now we can substitute or plug in F cosine theta in terms of our Fx. So we have F cosine of theta minus Fr equals ma. So the goal is to isolate the pulling force because we want to find the pulling force when the acceleration is 0.40 meters per second. Okay. So what we can do is, again, to move the retarding force to the other side of the equation, or to the right hand side of the equation, and that makes it positive. When we do that, we are going to have F cosine of theta is equal to the accelerating force plus the retarding force. Now we divide both sides by cosine of theta. So cosine cancels out, and then we are left with the force, or the pulling force, F equals ma, which is the accelerating force, plus Fr, which is the retarding force, divided by cosine of the angle. Now we can plug in those values. We have the mass given to us as 25 kilograms. So we have 25 kilograms times the acceleration, which is 0.40, and then plus the retarding force, which is 30 newtons, divided by the cosine of 30, which is 0.866. Now, if we evaluate this, it is going to give us a value of 46.2 newtons, which is about 46 newtons. All right. So we've seen the two cases where we can apply Newton's second law. In the first case, where the speed is constant, and we found the pulling force to be about 35 newtons. And then in the second case, where acceleration is not 0, we found pulling force to be 46 newtons. And this makes sense because if you just set the wagon to move at a constant speed, you just need to overcome the retarding force plus just some little force. And we can see the difference between the retarding force and the applied force, or the pulling force, is about 5 newtons. So we needed just that 5 newtons to set this wagon and the load into constant speed motion. However, if we wanted to move more faster or speed up, we need to apply more force. And we can see in the second part that the force is about 46 newtons to make it accelerate at this 0.40 meters per second squared rate. I hope you enjoyed this problem. And if you are new to this channel, please like, share, and subscribe. And also, if you are already a member, Thank you, and keep liking and sharing so we reach a maximum number of people that are in need of such resources. Until then, I'll see you in my next video. Bye bye.